Hey everyone, in this video I'll solve some sample questions involving a commonly used gas law known as Boyle's law. So let's do a really quick recap of some of the things that Boyle's law tells us. First of all, it says that the pressure of a gas is inversely proportional to the volume at a constant temperature, which means that if the volume goes up, the pressure will do the opposite and go down. Or if the volume goes down, the pressure will again do the opposite and go up. This video is going to focus on the mathematical side of this, where we can use the equation P1 times V1 equals P2 times V2. The ones imply the initial pressure times the initial volume where you start. The twos imply the final pressure and the final volume where you end. So here's our first sample question involving a sample of helium gas being compressed from 200 milliliters down to 2.4 milliliters. And that's a good example right there of what Boyle's law is all about. We've got a changing volume, which will result in a changing pressure as well. It goes on to say that before the compression, the gas was under atmospheric pressure of 1 atmosphere. Assuming the temperature remains constant, what is the pressure of the gas after the compression took place? So let's clear a little room here so we've got some space to work and solve this problem. Now, the first thing I like to do with any word problem is just pause and take a moment to circle any numerical value that I'm going to have to plug into the equation later on. So I've got 200 milliliters, 2.4 milliliters, and 1 ATM. If they're circled, it's always a lot easier to find them. The next thing I want to do is label what type of value they are so I know where to put them in my P1, V1, P2, V2 equation. These are both milliliters and those are both volumes, so they're both going to get the label of a V. Now, it will also be helpful to know ahead of time, are they V1s or V2s? Since it's going from 200 down to 2.4, I'm starting at 200, so that's my initial volume or my V1. And the 2.4 is what it's going to end at, so that's my final or new volume, so I can also call that a V2. This 1 atmosphere value is definitely a pressure because it's in ATMs. I'm not sure if it's a P1 or a P2, so let's go back and reread the sentence. It says, before the compression, the gas was under atmospheric pressure. So before is telling me that's an initial pressure, so I can label that as a P1. Now that everything is labeled, I can take these numbers and start plugging them into my Boyle's law equation. First thing we'll plug in is, of course, the value for P1, which we figured out is 1 atmosphere or ATM. P1 times V1, we said the first volume is 200 milliliters. That's the volume the gas is starting off at, 200 milliliters. Set that equal to P2. I don't have a value for P2, but that's because that's what we're going to solve for in this equation. Notice what it's asking. What is the pressure of the gas after the compression? So after implies what's the new pressure, or P2. When the volume has changed to a V2 that we figured out already is 2.4 milliliters, so we go ahead and plug in 2.4 for that V2. From here, you'll just follow some simple algebraic steps to solve for P2, almost like it was an X if this was an algebra class. So let's first simplify down these two numbers, 1 atmosphere and 200 milliliters. And that's a nice easy one because 1 times 200 just gives me 200. The next thing I want to do is get P2 all by itself on one side of this equation, so probably smart since this is multiplication. If I divided both sides here by 2.4, so there's my dividing by 2.4 on the other side, that'll of course cancel out the 2.4s here and leave me simply with P2 equals whatever this term gives, 200 divided by 2.4, which gives me a final answer of 83. Now the question remains 83 watts. I know this is a pressure, but is it atmospheres, is it kPAs? The way this equation works is the pressure units, or any of the units, will always match on both sides. So since my P1 that we used was ATMs, when I solve for P2, it will also be in ATMs. So the pressure of this gas after the compression took place is now 83 atmospheres. And let's look at one more example that's a little bit more complicated. This one says that a sealed syringe, so that's just, here's an image of a syringe. If you're not sure what that means, you can fill a syringe with air or any kind of gas. So this syringe is filled with 500 milliliters of air at 0.85 atmospheres. And then it says what volume is required for the air in the syringe to reach a pressure of 250 kPa, assuming that the temperature remains constant. So let's clear a little space and start working through my steps. First of all, circling all the numbers I'm eventually going to use: 500, 0.85, and 250 kPa. Let's label what these are. Milliliters is a volume and ATMs is a pressure. If we can put in the ones and twos, that would be helpful. I'm thinking these are both ones, V1 and P1. It sort of sounds like it's describing where we're starting, like an initial set of data points. So my first volume and my first pressure. It then says what volume is required for the syringe to reach. So now I've confirmed that these two numbers were the initial quantities because it says to reach a pressure. So this pressure is the new pressure after we change the volume, so I know that this one is a P2. Now with those variables labeled, I can plug them into the equation like you see here. Now you might have noticed that we have a problem with some of the data plugged into this equation so far, and it has to do with this idea from the last example that the units must match on both sides of the equation. And right now, my pressure on one side is ATMs, but on the other side it's kPa. And you can't plug in different units. They have to both be the same. So I could either change my atmosphere to kPa, so it matches the P2, or I could change the kPa into atmosphere so it matches the P1. It doesn't matter which you choose, but you have to change one of them over. So my choice is going to be to convert 250 kPa into atmospheres using our conversions, which I've got at the top of the screen. So I'm just going to move off to the side and clear a little space to write this conversion. I'm changing 250 kPa. We're going to do that conversion using dimensional analysis. So kPa has to cancel top to bottom. And I'm trying to change that into atmospheres on the top. That conversion we can find from this list of units at the top of the video that says 1 ATM is equal to 101.3 kPa. So the 101.3 goes on the bottom, and you simply have to divide and find out what this pressure is in atmospheres. After dividing, we find out that 250 kPa is 2.468 atmospheres, which I'll substitute in to the P2 in my equation. So here's how it looks with the 2.468 substituted in for 250 kPa. From here, I can go ahead with the algebra, simplify this down to get V2 all by itself on one side of the equation. I'm going to do that by dividing both sides of this equation by the 2.468. That'll cancel it off here, and then I just have to do the same thing on the other side, divide by 2.468. When I'm all done, V2 will be all by itself on one side of the equation. I just have to do the math over here, 0.85 times 500, then divided by the 2.468. This gives me a final answer of 172. The units that this will have should match the units on the other side. Since my V1 was in milliliters, my V2 will also be in milliliters. And that concludes this video on Boyle's Law problems. Hopefully you found it helpful, and thanks for watching.